So thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Samson Wang, who will tell us about quantum computational complexity of matrix functions. So Samson is a postdoc at the Institute of Quantum Information and Matter at Caltech. He completed his PhD under Mario Berta in Imperial College London and was a visiting researcher with Simon Eipers in IRIF. And his main interests are in the theoretical aspects of quantum algorithms and near-term quantum computing. So Samson, the floor is yours.
Okay, wonderful. Thank you so much, Joe. And yeah, thank you for this kind invitation to talk today. Yeah, I'm very happy to talk a bit about our work on computational complexity of matrix functions. So if it's all right with everyone, I'll just get right into it. One thing maybe to say from the start is please feel free to interrupt with questions. In particular, I was told maybe there'd be a bit more of kind of like a broad audience. So particularly if there's some like basic definition I haven't defined or I've missed, please do shout or interrupt me with any other questions you have. Okay, so let's see if the slides work. Great. Okay, so the realm in which we'll be thinking in this talk is the realm of kind of quantum algorithms for processing large matrices, right? Now, a lot of problems that we hope to use quantum algorithms for can be thought of as enacting functions on some big matrix, which we denote here as A. That's an n by n matrix, right? So for instance, HHL, the so-called HHL algorithm for linear systems, could be thought of as enacting the inverse function on the matrix, right? Time evolution, the canonical quantum algorithm, if you like, can also be thought of course, as a matrix function of the complex exponential. We can think about quantum walks, where you might be thinking about enacting some polynomial, particularly the Chebyshev polynomial on a matrix, or even eigenvalue finding and phase estimation. In some ways of casting it can be thought of as applying some function on a matrix, right? Now, in this frame of thinking, all of the algorithms I've mentioned and a lot more algorithms have kind of been unified under the so-called QSVT or quantum singular value transform framework, right? And the idea is that the QSVT allows you to enact a large class of polynomials of some given matrix under some specified access model. And by looking at kind of standard kind of polynomial approximation theory of approximating other functions with polynomials, this leads to efficient algorithms for these problems. And when we say efficient here, what we mean is under certain specified conditions, the algorithm basically runs as kind of order polylog n, where n is the dimension of the matrix, as we mentioned before, right? So this is very nice and a very kind of unified, kind of mature framework in which we can think of quantum algorithms, right? Now, just because we have a quantum algorithm doesn't necessarily mean that, we have some use for it, right? Specifically, a basic criteria we might want is that it has some, strong advantage over classical algorithms, right? So now that we have this wonderful tool to kind of look at a broad class of quantum algorithms for matrix functions, we might ask, like, where precisely can we actually find exponential quantum speedups, right? And this will kind of be the focus of this talk. And the way that we'll look for areas of speedup are to think in two directions, right? So the first direction is to think about classical hardness. So where might we suspect things to be hard classically, right? And the tool that we'll use here are the tools of complexity theory. And this is a kind of worst case analysis of problems, right? And the two key kind of terms that we'll be using are the notions of BQP hardness, right? And so this kind of colloquially can be described as meaning basically, if a problem is BQP hard, it means that you can use it to simulate any polynomial quantum circuit, right? So it's at least as hard as kind of polynomial quantum circuits. The other notion we'll look at is BQP completeness, right, which is simply BQP hardness plus the fact that it's quantumly efficient to solve, right? So if you combine these two facts, that something's quantumly efficient to solve and it can simulate any polynomial quantum circuit, this is in a sense basically equivalent to the class of polynomial quantum circuits. And in doing so, also, we would think of this under standard kind of assumptions as probably being hard for classical algorithms, right? So the other direction in which we will kind of investigate possible areas of speed up is to identify areas of classical easiness, right? Where like we don't suspect there to be quantum advantage. And to do this, we will simply kind of investigate new classical algorithms, right? So in our work, we kind of catalog a broad class of problems and kind of investigate them from both ends and kind of tighten results and prove new ones. Now, just to say a bit more about kind of how we're kind of identifying possible areas of advantage, right? It's complexity theory is kind of a very powerful tool, but constrained in many ways, right? And so generally, when we prove complexity theory results, as I mentioned, these are kind of worst case analyses, right? So what we'll actually concretely do is we'll kind of draw a circle around kind of a set of problems, like we'll identify a set of problems. And we'll ask within this set of problems, how hard are the hardest problems within this set, right? And this is usually all we can really kind of say concretely. And in this sense, it's a kind of worst case analysis. And so to prove tighter complexity theory results, we should then identify kind of ever smaller and smaller kind of sets of problems, more tightly constrained classes of problems, and see if they still remain hard. Or indeed, if we make it too tight, we might in fact make it easy. Right? And it's in this kind of framework that we'll be kind of thinking. Right. Now, when we mention complexity theory, this already conjures up a notion of a computational model. But we can be more precise here of exactly what kind of computational model we're dealing with, right? And so in thinking about quantum advantage, many different models or frameworks have been considered, and I'll mention two here. So the first is that of kind of like Oracle query complexity, right? This is a setting where you're imagining your classical algorithm and your quantum algorithm to call a respective classical or quantum oracle. And we would prove separation results based on algorithms with access to these tools, right? This is a neat, framework for theoretical insights, and indeed many important insights have been proven in this framework. But the complexity of the problem can be hidden in an oracle, right? Because a quantum algorithm is given access to a different oracle than the classical one. And so if we want to think about more kind of concrete problems, maybe shifting focus a little bit or motivated a little bit more to kind of real world problems, we might, this might not be the most favorable model to kind of think of. Another kind of model that has had a lot of interest in the last kind of 5-6 years, that was kind of started by Ewan Tang, was these kind of quantum inspired algorithms, right? So here we're thinking of classical algorithms which are given a very special kind of oracle, kind of sampling oracle, that's meant to kind of mimic quantum oracles, right? This resolves some of the problems of the previous, right? Which is that it's a more fair comparison. And this is kind of a nice framework to think in. However, like these oracles are not necessarily efficiently instantiable, right? And so again, if we're more motivated by thinking about really concretely, like what algorithms could we run like efficiently, this isn't necessarily the best framework to think of, even though it's a very insightful one and useful for other reasons. Okay, so to that end, what kind of framework do we look at? So we're kind of motivated for problems where really we're starting with classical input and ending with classical output, right? And when we compare classical and quantum algorithms, they will be given the same input, right? They won't be given different kind of inputs. And in both cases, the input will be classical. And so specifically, we're looking for computational speedups where the data access, which in this case would be a matrix, access to a matrix is efficiently implementable for our problems, and the same input is given for our classical solver and our quantum solver. Okay, so to this end, kind of what problems do we look at in our work? First of all, to mention, just to make it clear, when we say matrix function, what we mean here is an eigenvalue transform, right? So you're actually enacting like a function onto the eigenvalues of the matrix. And we'll kind of look at two kind of rudimentary problems, or kind of quite elemental problems for matrix functions, right? So the first is perhaps the simplest thing you could try to cook up, which is that I've enacted a function onto my matrix, and then I'm just going to ask for one matrix entry from this problem, right? So the output is just kind of one number, right? The second problem we'll look at is a local measurement problem, which crops up in a lot of settings where we're basically enacting a map corresponding to this matrix function. In this case, for simplicity, enacting it onto the all zero state. And then we're just going to perform a local measurement, say, for sake of argument, and in this case, written on the slide on the first qubit, right? So kind of rudimentary kind of local measurement where you're looking at the action of the map corresponding to this function. And in both cases, we'll look at these problems where we ask for an approximate solution to these problems up to, say, additive precision. Now, these problems will have a number of problem parameters, which will really kind of determine the complexity of the problems. So, of course, there's the function itself, and we will look at different classes of polynomials of degree d. We'll look at the classic linear systems function, which is the inverse function, and we'll look at the time evolution function. The matrix norm will play a big role in the complexity of these problems. And so what this will materialize as are constraints on different norms of the matrix. And so we'll look at constraints on the operator norm of A, as well as constraints on other kind of norms, which I've just kind of denoted generically here as the data norm of A. And going back into this picture of kind of looking at ever more restrictive classes of problems, generally people will prove complexity theory results for the set of problems for which the operator norm is bounded by 1. But you can, of course, set other more restrictive constraints. So for any larger norm, if you set the constraint that is bounded by 1, that's a smaller class of problems, right? And a more tightly constrained class of problems. And the complexity may change if we change this constraint. We'll look at, of course, the error, and the size of the error that you require will also play a role in the complexity. So specifically, we'll look at how large the inverse error is. The sparsity of the matrix plays a role. And there'll also be other kind of problem-specific parameters, which are specific to the function of interest. So for instance, if you're looking at polynomial, the degree plays a role. If you're looking at the inverse function, the condition number is an important parameter. And of course, the evolution time in the case of time evolution. And so, as I mentioned, typically complexity results are proven for this setting, this constraint on the norm where the norm is just bounded by 1. However, you could imagine, like, you might see this complexity theory result and think, oh, super, like maybe this tells me something about the hardness of the problem. But if you actually encounter like a problem in the wild that you would like to maybe use your quantum algorithm for, it might have matrices with kind of different properties and different norm constraints. Typically, also, all other parameters are considered to be scaling polynomially in input size, where by input size, I mean polylogarithmic in n, the kind of dimension of the matrix. What we'll do in this work is we'll kind of vary these parameters individually and see how the kind of complexity changes when we're not in this kind of traditional setting of setting the parameter size. Now, there's one more kind of parameter or hyperparameter, if you like, which plays a key role in the complexity. And this is the data access model, right? So we've kind of touched on this briefly, but not explicitly, right? And this is like, how are you actually going to access your data? In which case, in this case, being a matrix, right? Now we asked for efficient access to the matrix, to the matrix, right? Where efficient, we recall, means in order polylog n time. And now the standard way to people think about this is this notion of sparse access, and this is access to your matrix in the computational basis. So here we ask that there exists an efficient function to compute the non-zero row entries for each row, right? So in general, we might think of like a sparse matrix, and if there's no structure to this sparse matrix, right, you would have like very many elements in your matrix, right? And so like actually even just kind of writing your matrix down or kind of describing it is inefficient, right? So actually, if we ask for efficient access to a matrix, we need something much stronger. And so this is one such case, right? That like all the kind of non-zero entries of each row are kind of efficiently computable somehow. Another kind of access we could think of is in a different basis, so the Pauli basis. Here we can presume that for some reason we know the matrix given in the Pauli basis, and this is more common, let's say, in physical problems, like where the matrix might correspond to a Hamiltonian. And so the access here is very simple. It's just a list of the Pauli coefficients, right? Where so by definition we would then presume there are only kind of polylog Pauli coefficients. One thing to note is that if you have Pauli access, you can then actually instantiate sparse access. So in this sense, Pauli access can be thought of as a special case of sparse access, but one that we might have strong physical motivations to expect to have, right, in certain problems. So with that, that kind of concludes maybe kind of setting up the framework in which we're thinking. Maybe I could pause at this point and ask if there are any questions up to this point. Otherwise, I'll kind of move on to describing some results.
I was just thinking, like, so how is the Pauli access kind of more efficient? You said that it could be like polylog.
So it's efficient in it's efficient. Well, we would constrain it to be efficient. So we're presuming that our matrix is describable as a linear combination of only polylog Paulis. So it's not that all matrices can be. Yeah, exactly. So in all cases, we're kind of thinking of some constrained class of matrices that can be accessed efficiently, right? And this is one example of that, which we actually encounter a lot in certain problems.
Okay.
Are your matrices
there's a question from John.
Oh, are your matrices self-adjoint?
Oh, sorry, do you mind saying that again? It was a little muffled.
Are your matrices self-adjoint?
Yes. They, for simplicity, we can say they're self-adjoint. We will generally think of self-adjoint matrices and maybe look at further kind of constraints. As we say, like if we're looking at computational complexity results, we can kind of try and make things tighter and tighter. So in general, we can always prove things for self-adjoint matrices, and we can actually do a bit more for complexity theory results and look at, for instance, symmetric matrices. And
thanks.
Okay, well, if that's all for now, then maybe I can proceed and discuss some results. So if you open our paper with the kind of same title, we have this kind of, I have to admit, a bit kind of intimidating looking table with just kind of too much in it, where we kind of tried to just survey and catalog everything in one table and kind of catalog areas of hardness and classical easiness, and kind of just lay it all out in one go. In the rest of the paper, we then try and like comb through some of the key ideas and takeaways and kind of in a more easy to pass format. And I'd like to try and do the same in a kind of talk format, because this is kind of too much to look at all at once, and kind of summarize things in kind of some key kind of takeaways, if you like. So the first takeaway is that when we kind of look at these different functions that we're thinking of, there's certainly like a hierarchy of hardness across different matrix functions, right? And so we can see this by looking at our different functions in two settings, right? And before I go into exactly what these settings are, if a certain parameter is not mentioned, I'll just say that we're kind of assuming it's taken its default value, which is that it's order polylog n, right, which is kind of the standard assumption. So when we remark on a parameter in particular, we're just saying we're constraining it more than the kind of normal default value. So here, when we look at matrices with constant sparsity, meaning in each row there's a constant number of non-zero entries, and we have a very strongly suppressed operator norm. So our operator norm is, oh, my apologies, there should be a 1 over polylog n here. So like, yeah, so the operator norm is not just less than or equal to 1, it's kind of 1 over polylog n in size. We find that for time evolution and for the inverse function, this problem, which are the problems of the matrix entry problem and the local measurement problem, are BQP complete, right? And for Chebyshev polynomials, we also see that they're classically hard under the kind of standard assumption that BPP does not equal BQP, that classical does not equal quantum. So that's kind of one result on its own. If we then look at a more constrained setting, an even more constrained setting, an even more generous setting, so a broader class of problems, which should be kind of quote unquote harder. So we allow our sparsity to now be polylog, so we can have many more non-zero entries per row, and we have a much more gently suppressed operator norm. So now the operator norm of A can be kind of order 1. It turns out monomials are kind of classically easy, right? So kind of not all functions are certainly born equal, right? We find similar results hold in Pauli access, so they're kind of robust to this more constrained setting of Pauli access. And we also find some similar results when we look at kind of different norms, so like the induced matrix 1 norm. The second takeaway we have is that, you know, special cases of access model can actually make problems easy. So before we saw that, you know, those results that show like a difference between hardness between different functions is robust even if we look at kind of Pauli access. This is kind of not, you know, not all properties are robust in this way. And so this is one example. If we think in sparse access, it turns out all functions are BQP complete if we look at constant sparsity and then all other parameters to their default settings, right? Okay, so this means that if we look at this broad class of problems, you know, like certain worst case problems are going to be classically hard, but still quantumly easy. However, if we look at Pauli access, you can increase the sparsity beyond constant, and actually all the functions are classically easy, actually. And so this is saying that, you know, if you're kind of encountering some complexity theory result in the wild, and you maybe look at it and use it as kind of motivation, if you like, that some problem you're applying it to in the real world might be quantumly easy and classically hard. One might need to be a bit careful, right, of exactly how are you instantiating your sparse access, right? I'm actually kind of curious, like, different ways of instantiating sparse access, and personally, I'm not aware of like many, or if any, besides Pauli access or like quite conventional settings. And so, like, you know, you might be getting your sparse access because of some other kind of structure, and this structure might actually be causing your algorithm to be causing your problem to be kind of classically easy. Third takeaway is one that has been kind of, I guess, explored or framed in a few different settings, one being this Garibian and Legal paper on the guided local Hamiltonian problem. And that's just that quantum algorithms can obtain kind of exponentially better precision in some settings. So one example we give here is back to the monomial problem. We see two settings where you can get your monomial to kind of additive precision. And this is kind of classically easy, so classically a doable problem. But you can ask for an exponentially tighter precision. And this is quantumly easy and then actually now kind of suspected classically hard under standard complexity assumptions. So now I'd like to say a bit about kind of the tools that we use for proving things in both directions. And so first I'll discuss a bit about tools used for showing kind of BQP hardness. Right. So the key idea is we're going to work with something called a clock matrix. And our goal is to have some reduction from, for sake of argument, the matrix entry problem. So we thought about the matrix entry problem and the local measurement problem, but in this kind of what we'll proceed, we'll kind of think about the matrix entry problem as an example. And we want a reduction from that problem to the problem of computing outputs to quantum circuits. Right? And so in doing so, then we'll be able to show that, like, if we can solve the matrix entry problem for this class, large enough class of problems or matrices, then we can simulate quantum circuits. And that's kind of how this argument goes, which is a old idea and has been kind of used in many forms to prove similar results in the past. So specifically in this setting, this is what we'll do. So we want to simulate a measurement on a so-called BQP circuit. So this is just some quantum circuit, it's a polynomial sized circuit. And what we've done in this equality is just to isolate the first qubit. And by simulating a measurement, in this case, the zero projector of the output of this circuit, we just want to know about the size of alpha naught. So, the modulus of alpha naught squared. And we would call this simulating a measurement of this circuit, and we'd be satisfied. So we've broken on the right-hand side C into its elementary gates. So we say there are kind of T gates. And what we'll do is we'll define a new circuit. And this circuit will simply be the original circuit folded in on itself, where in the middle we've just inserted a Pauli Z on the first qubit. And we're just going to relabel these as these V operators, of which there are M of them. Now, we can already kind of note that if we look at the 0/0th entry, if you like, of this C prime, which is a matrix, if you add 1 to it, that is already alpha naught squared. Right? So this is the kind of quick and dirty way, if you like, to show that, like, there is some semblance in which you can quite easily get simulate, if you like, some measurement on a quantum circuit by solving some kind of matrix entry problem. Right. Now, in this case, we've not looked at some matrix function. We just looked at some matrix, which is this unitary, basically, which is this product of these V matrices. And a question was raised earlier about, like, what classes of matrices do we look at? Do we look at, Hermitian matrices or something else? And, so there are two things we would like to do from now on. We would like to actually look at some matrix function, and we would also like to maybe move away from unitary matrices, because you might argue, okay, unitary matrices are a large class of matrices. If there was one class of matrices you suspect some connection to quantum, it would be unitary matrices. Right? So in the next steps, we'll kind of speak to these points. So let's show how we can relate the matrix entry problem to simulating quantum circuits for monomials, sake of argument. Right? So what we'll do is we'll again look at these V operators, which, as we recall, were kind of the gates in our circuit kind of folded in on itself with this Z matrix, Pauli Z in the middle. And we're going to append a register in front, which we'll call like a clock register. And what this clock register will do is it'll just kind of walk up kind computational basis element of your clock register up one step each time, right? So this has the property that if you take an m-fold product of this now clock matrix, you'll get the operators displayed on the screen. And this is a kind of interesting property that now if you look at the 0/0th element of this will tell you about alpha naught again. Right? So this is kind of how we can massage the monomial problem and relate it to the matrix entry problem. Now W is still a unit, or is now like a complicated operator, and we might want to look at kind of different classes of matrices, for instance, Hermitian matrices. Right? So how do we do this? But this is quite simple. We can just define a Hermitian matrix A, which is W plus W dagger with a normalization, and try something similar. And the math will get more complicated, but you know, something will come out that will be useful to us. And so we use the fact that W to the 2m is the identity matrix. And this kind of fact that helps with some spectral analysis. And if you kind of crunch through things, we'll find that for the matrix monomial problem, or indeed any kind of function, which I've now written in kind of generality. So for any function, the kind of 0/0th entry can be related to some kind of little mess of things, where on the right-hand side, the key thing is that we see there's the alpha 0 squared coming out at the front as a coefficient, right? And so this is some relation between the matrix entry problem and the output to our quantum circuit. We'll notice everything else is just kind of a number and kind of easy to compute, right? It's just a function of, it's a scale, that's now scalar functions, right? And so this is something that you can actually kind of evaluate. And so this kind of trick had been used before for monomials, but what we did in our work is kind of to generalize it to more general kind of functions. And so for any function, this can now be a kind of test, if you like, for BQP hardness. So concretely, after some refining, we can write a general condition to test for BQP hardness for the class of symmetric matrices, which are also 5 local. And so this is kind of smaller and smaller kind of constraints of matrices that we can try and squeeze out. And then the condition will read basically as follows, right? And this is what the equation that's on the slide is basically the equation on the previous slide, but just kind of simplified a bit. So it turns out that if you can compute a matrix entry of f of a to some desired error, that's kind of omega of k, this problem is BQP hard if the odd component of the function satisfies this kind of stated condition on the slide. Specifically, if this is satisfied for some m, which is order polylog n. And this m parameter is actually the number of gates you're effectively simulating. So you can also use this condition to argue something about the power of simulating another kind of specified size of or number of quantum gates, right? But specifically, if we want to say BQP hard, it just simulates a polynomial number of gates. So we choose m is polylog n. Right? And to emphasize again, this is just some like kind of scalar condition. You can just kind of check for your whatever function you're kind of interested in and just kind of plug it in. Great. So what I will end on is so this was kind of tools to prove BQP hardness. What I'll kind of end on is going from the other side of what are some of the kind of tools we use to show kind of classical algorithms, right? So primitives for our classical algorithms. The first, which is what we use to kind of show our results related to kind of exploiting Pauli structure, is the following. So we have some kind of polynomial eigenvalue transform for matrices specified in the Pauli basis when the matrix is especially sparse in the Pauli phases, right? And so the result is as follows, which is that if I have a degree m matrix polynomial, then I can return this degree m matrix polynomial in time polynomial in m, but exponential in the number of Pauli terms, right? So if the number of Pauli terms is kind of very small, then this is an efficient algorithm, and moreover, it's actually exact, right? And so this can recover not only monomials but more complicated or so-called maybe more quantum polynomials such as Chebyshev polynomials efficiently, right? And this is based on a simple observation, which is that if you don't have many Pauli terms in your matrix, and you want to look at some polynomial of this matrix, the set of Pauli matrices which it explores, or the kind of orbit of Pauli's, is kind of constrained, right? And it's kind of, no matter how high your degree is, kind of it'll be kind of constrained. And indeed, the set of Pauli's you obtain from a kind of product of Pauli's with only L terms goes as kind of 2 to the L, and it's exactly the set that's kind of written on the slide. The second tool we use kind of at length is kind of Monte Carlo sampling ideas, which have kind of been around for a while, which is that you can get a degree m monomial with a kind of Monte Carlo sampling routine. And the way to do this is that if you can normalize your matrix in with a sufficiently large norm, then you can kind of sample from matrix monomials and then use those monomials to build other functions. And so the relevant norm in sparse access is this kind of induced one norm of the matrix A, which is kind of the largest column sum of the matrix. And in Pauli access, there's a kind of analogous norm, which is this kind of Pauli norm, which is the one norm of the Pauli coefficients. The last kind of remark on things that can be exploited for classical algorithms are kind of, again, looking at monomials and then using monomials to build other functions. And the observation is that you can get any degree monomial if you have constant sparsity, if your operator norm is a little bit below 1. Right? And the key observation is that if your operator norm is a bit below 1, then your maximum eigenvalue is bounded. So larger powers of like higher power monomials have contributions which decay quickly, right? And so you can actually kind of truncate and then use kind of exact sparse matrix multiplication to recover the lower powers and then kind of forget the higher powers. So those are kind of some of the tools we use. And so to that end, I might kind of conclude because I see that we've kind of reached 40 minutes. So in this talk, we've kind of cataloged quantum and classical complexities for different matrix function tasks. And kind of took out the main takeaways, I think, from our kind of broad catalog. And we've covered, a spectrum of functions where each one can be thought of as building blocks in their own way of other functions. So people have been thinking of QSVT and using polynomials as building blocks of other functions, but you can also think of the time evolution function and actually even the inverse function as also kind of building blocks of other functions. And so far, we've been toggling lots of so-called global kind of properties of the problems, right? So we're not saying much about the kind of internal workings of our matrix A. We're looking at the norm, the sparsity, these kinds of things. So one kind of problem that I'm curious about is, if you know more about the properties of your matrix, for instance, you know that it's local or geometrically local or have other properties, does this kind of also open up more room for classical algorithms? I'm also curious, what other kind of useful examples of this efficient sparse access do we know? And do they kind of also potentially render some problems easy as compared to worst case, right? because this would really tell us how informative, for instance, traditional computational complexity results are for us if we actually want to kind of think about concrete problems. I've realized I've said these bullet points in reverse order that I've written on the slide, but one thing I can mention is this, for instance, this Chris Chen and Garnet Chan work recently, where they do actually think more about the internal structure of the matrix for some chemistry problem of disordered electrons, right? And I'd been in communication with them for a bit through the project, and so at first I think they were looking at these kind of banded matrices where they thought that if you could look at some matrix function on this banded matrix, this might be like a easy problem for quantum but hard for classical. But Chris then made an interesting observation, which is that if you have a banded matrix, so a banded matrix is like a sparse matrix where you're told that all your matrix entries are kind of in a diagonal band around the main diagonal. If you have a banded matrix, then if you look at kind of matrix monomials, then the band grows kind of linearly in the degree of the monomial. And so things like sparse matrix multiplication are actually a lot more efficient. And it turns out that there are then efficient classical algorithms for matrix polynomials on this kind of band matrix. And then so this kind of unfortunately kind of dashes hopes of kind of exponential advantage in a lot of settings for that type of matrix, for example. So this is I wanted just to highlight this was a kind of more interesting, like kind of concrete finding that came out recently. And so with that, yeah, I'd like to conclude and thank you for your attention. I'm happy to take any questions.
Okay, thank you very much for a very informative talk. Yes, so we have quite some time for questions. So if you have a question, just feel free to unmute and ask them now.
Yeah, hi. Thank you for your talk. Maybe just on the problem setting. So you're considering both quantum and classical oracles. Is that?
We're not really in an oracle model, and there aren't any quantum oracles, right? So the input to our classical and quantum solvers is the same each time, which is a kind of classical description of our matrix, and this description is an efficient one. So we're in both cases we're given a classical input, which is in the case of this sparse access, some function which efficiently gives us the non-zero entries of each row. On Pauli access, it's just like a classical list of the Pauli non-zero Pauli coefficients. So we didn't really kind of consider an oracle model in our setting. Yeah.
Okay.
Okay. Right. So do we have anyone else? Okay, maybe I can ask something for now. So like because you talked about the matrix entry, right? So that one, I guess, like involved this clock matrix. Would the local measurement problem involve the same clock matrix, or there's something different there?
Yeah, it's a similar idea with a slightly different matrix, but certainly kind of similar techniques. So originally when some of these BQP complete results were shown, they were mostly in the for the local measurement problem. And so there's a long line of literature which kind of uses that idea, and indeed is a kind of clock matrix, but with things a bit tweaked specifically for that problem.
Right. Let me see if there's anyone else. So maybe sort of like in a kind of more conceptual, general. Oh, wait, I have Taiga here. Yes, go ahead, Taiga.
It might be ridiculous question, but so in computational complexity, so we have BQP-complete problem, right? But does there exist some kind of average case hardness of complete problem? So I mean, this the BQP-complete problem, for example.
Yeah,
Does
yeah,
someone consider it?
that's a great question. And like traditionally, kind of average case is quite hard to deal with, and so it doesn't kind of fall into the same kind of neat structures. But certainly this is like of great interest, that if we can like actually find problems that are average case hard, this is a lot more powerful and potentially informative, particularly if we're trying to think about things that might be more like heuristics, right? It's a lot more powerful if, you know, we have a class of problems which we can say are average case hard, or maybe, but like quantumly easy, and if we have a kind of more heuristic type algorithm, like an optimization algorithm for this, right? That can be very informative. But the only snag is it's very hard to set up a setting where you can actually kind of prove average case hardness, right? Which is why most people
I see.
worst case. Yeah.
Thank you very much.
Right. Let me see if there was anyone else. Okay, what I wanted to sort of ask is kind of like maybe like kind of your own opinion. So after like doing this work, so what sort of like have you learned about like how hard or how easy it is to actually find this kind of problems where, I mean, ultimately our goal is to find useful practical problems where quantum actually helps us, right? More than classical methods. So kind of like, what is your takeaway from getting involved in this work with regards to this kind of problems?
Yeah, that's a good question. I think there are lots of challenges ahead for us, right? So even just forgetting whether we like expect strong quantum speedups, even just kind of finding concrete examples of problems in the quote unquote real world, which can be kind of mapped to a quantum algorithm and be solved efficiently, with some hope of maybe speed up, is difficult. And these are kind of there are a lot of kind of well spoken about kind of caveats to a lot of these quantum algorithms, which make things murky. So for instance, in the linear systems problem, of the kind of condition number coming up, of the output of your quantum algorithm being an issue, right? So like that you kind of return a quantum state, but kind of what in the classical world, like what information do you actually want from your quantum state? Do you just want to make a measurement? Do you just want like one entry of your state, and these kinds of things? So I think even in identifying like concrete applications, I think there's a kind of dearth there, and that's a challenge, and that's without even speaking like very concretely about like kind of provable advantage. So I think something that would be great is if we can somehow cook up more kind of potential applications for these settings, or as was alluded to by a great question by Tiger, is as like kind of seeing in what settings could we maybe think about average case hardness, or things that look more like heuristics, where we have quantum heuristics, where we have some reasonable hope that maybe they're kind of useful, but they're not maybe provable, kind of like end-to-end guarantees. Right.
Yeah, I think that's fair. Yeah, Yeah, I mean, like I guess like sort of like I'm not so familiar with the results, of course, but I always had like this impression that there's a lot of things that's hidden when you have all of these caveats, and then like how you are able to like how you represent your inputs and things like this, and it's not always clear that where your kind of advantage is coming from, because maybe a lot of the work is being done by the caveat itself in some sense.
Exactly right. Yeah, that's true. And
Mhm.
like a lot of the conditions we just don't even know if they are like satisfied or not, right? Like we could think of some problems where, like, for instance, going again to the linear systems problem, like there's this condition number dependence, this kappa that I showed on an early slide. And sometimes maybe you just don't like you might be thinking about a class of problems where you just don't really know how the kappa is going to behave, right? So like we wouldn't even be able to like predict beforehand maybe like how well these outcomes would do.